Okay, welcome back to part 3 of IP addressing and routing review. So in this video we'll be going over the packet forwarding process and the sources of routing information. So once again, this first chapter should be purely review from CCNA material, just in a different format. So we'll have a look at how we forward packets through this network. So we'll be concentrating on layer 3, and just remember this is key to troubleshooting for you to understand how devices use decisions on forwarding information. And we'll always refer back to the OSI reference model and the 7 layers. So basically, using a ping, the ping will tell you whether you've got connectivity through layers 1 to 3. So this one, topology wise, we have a PC over here coming across to a server. So we'll be looking at how this works its way through and the steps taken in its travels. So to start off with, we will try to get to the server. Now, cast your mind back. Layer 3 needs layer 2 to be able to forward information. So when we look at the information, we have, in this case, the Ethernet headers, which is layer 2, source and destination MAC addresses, and then layer 3 headers, which are source and destination IP addresses, and then we have our TCP transport protocol and data encapsulations. So just remember, we need an association of layer 3, which is our final destination, and layer 2, which is our next hop. So the next device that needs to action the packet as it travels through the network. So first off, for PC 1 to actually send it anywhere, it needs to be able to forward it to the gateway, because it knows it's not on the same network, so want to send it to its gateway. Now, if the MAC address for the gateway is not in its current MAC address table, it'll use ARP, Address Resolution Protocol, to request the MAC address. So I'll send a request, get a reply. Once it has the reply, it now has the information to form the layer 3 and layer 2 headers, and it can start forwarding. Second step is when router 1 receives that information. So it will tear off the MAC address layers. It'll look at the IP addresses to work out where it's got to send it to, but it also looks at the time to live field and decreases it by 1. So if it reaches 0, it throws the packet away because it's timed out. If it still has a value greater than 0, it'll then look up that routing table, and in this case determine that it needs to forward it to router 2. So it then puts the appropriate layer 2 headers on and sends it on its way. Now, rinse and repeat for router 3. It'll come in, decrement the time to live header field. Then, again, if it's above 0, it'll look up its routing table to find out what to do with the packet. In this case, it knows it's sending it out fast Ethernet 00, and it knows that it's on its final destination, so it'll do an ARP request to get the precise MAC address of the destination, and then repackage it in layer 2 and send it on its way. So, what's in the routing table? So, routing table is basically a list of networks and the interfaces or the next hop that it needs to send it to get its destination. When it's doing a lookup, it'll look for the longest prefix match that it can find. So if it's got the same networks but one's /8, /24, or /26, it'll try to find the address that has the most bits. Okay, so by matching more of the IP address against its entries, it gets a more accurate match, so it can send it to its best destination. So the MAC address table in routers are just like any other MAC address table in a PC or any other end device. It is a entry of IP addresses and MAC addresses associated with that IP address, and this is what the device uses to fill in those layer 2 headers before putting it on the wire. So each layer 2 protocol will have its own naming or addressing structure, whether it's Ethernet, multi-point frame relay, dynamic multi-point virtual private networks. Now, is that a mouthful or what? So it all comes down to the protocol. Remember, IP doesn't care about the transport method. Okay, it will use point-to-point networks, Ethernet, frame relay. It's not technology dependent. So Cisco has this little shortcut which it calls Cisco Express Forwarding, and this enables it to have more information on hand in the data plane, so it doesn't have to continuously go up into the control plane to get information. By doing this, it is able to forward information faster to the destination. So Ceph uses a forward information base, which is basically the same as the IP routing table. In addition to the information that's found in the routing table, it also adds multicast and direct connected routes. The other thing it does is it basically pulls down that MAC address table and what it's called a adjacency table. So this has the frame header information required for the framing of the packet. Okay, so if it needs an interface and the next hop MAC address, that's all there. whereas if it's a point-to-point interface where it only needs to know the exit interface, that's what's there. So it pre-populates, if you like, the header information so that it doesn't have to continuously look them up. It already has the associations there for the adjacencies. So troubleshooting, well, there's a few different ways of looking at information from the routing table, and one of these for Cisco Express forwarding is to be able to see what's going on is show IP route and then the address that you want to determine the route for. So in the output, it will give you the actual network address. Now, because it's associated with a routing protocol, it'll tell you how it learnt the protocol. So it's administrative distance, it's metric, etc. Everything required to know about the routing protocol that it's learnt the route from, how long ago it was updated, and then it'll tell you the actual forwarding information. So there it is, it's from this network via this interface, its metric is there, and so it has a good bit of information for you to build your knowledge of how it's forwarding. So if you want to get more information explicitly on the CEF process itself, we can do the show IP CEF and the address. So you can see here there's less information given in the output, but it still has the next hop and the egress. So all that information is precise and easy to follow. So if you use show IP CEF exact route, then give it the source and destination addresses command. It'll give you the mapping that it has. So it says it was sourced from this address, its destination is this address, and then it'll tell you the egress interface and the next hop. To look at the MAC address table, we use the show IP ARP, which will give you the mapping between the IP addresses known and their MAC address. And I'll tell you what interface these are associated with. So to look at the express forwarding adjacency table, we use the show adjacency detail, and this will give us our precise information on each adjacency known to the device, and it will have a value that represents the interface, and this is a hexadecimal value, and it includes the calculations for the IP address and the associated information for the MAC address. So here, FR map, so that's a frame relay map. So frame relay uses a DALSI number for its layer 2 address. So it will provide all this information in this calculation. So we can go through and get used to understanding how to read this information. It's not natural to read and decipher it. We just need to know how these addresses are formed, and then we can use some backward engineering. Okay. Next up, sources of information. So this is how our routing tables are structured and shared. So when information arrives from a routing protocol, it's coming into the device. It comes into the data structure, so it formulates the correct information structure so that it can then be put into the routing table if it doesn't already have a route for that. So you can have multiple paths to the same destination. So within this data structure, it'll list them all together, and then it'll take the best routes from this data structure and inject them into the routing table. The routing table doesn't include every single path, it only includes the best. This information will come from any interfaces that are enabled for this particular protocol, whether it's OSPF, EIGRP, and many others that are out there. Static routes and directly connected routes are directly injected into the routing table because they're a manual input. And then from here, from the IP routing table, if we are doing any route redistribution, which is taking routing information from other sources of information outside of the routing protocol, so those static routes, and injecting them back into the routing protocol, and then it'll again send the routing information out of its interfaces. Notice it doesn't go back via the source of information. Okay, comes in, goes through this process, and then goes out. Okay, routing updates going back to the source do not include the source information, so it's selective about how it forwards, so it will not form a loop. Now, here's a list of some of the protocols and their administrative distances. So what's an administrative distance? Well, it's a measure of how trustworthy the source of information is when comparing different protocols together. The lower the administrative distance, the better the source of information. So if you look at here, directly connected interfaces are 0. They are the most trusted source of information because they are directly connected to the device and are active. Static routes are put in by us administrators, so we're trusted, number 1. Then you break it down into the various protocols. We will be looking at IGRP, which is Enhanced Interior Gateway Routing Protocol. Took me a second to remember what the abbreviation was. Okay, so we have summary, then we have border gateway protocols, and you'll notice as you go through that they are all got different addresses and there's gaps in between, and yes, we can manually adjust these if we need to. This brings us to the end of part 3. I look forward to seeing you in the 4th section, which is static routes and troubleshooting tickets. So until the next one, I'll catch you later.